Welcome to this week's second lecture. In the last lecture we have seen these special cases, and in the second lecture we are going to see the second case as well. Let us remember what the first special case was. So special cases, case 1. So in this case we had an A matrix which is in Cn by n, and we have a single eigenvalue. I have called that lambda I, and remember in this case we also have said that d of s is equal to m of s. Okay? Characteristic polynomial is equal to the minimal polynomial. So if I write d of s here, it is going to be s minus lambda I to the power ri, and m of s is going to be s minus lambda I to the power mi. But ri is equal to mi in this case because of the equality, so this is ri. And furthermore, the characteristic polynomial should be an nth order polynomial. So that means that ri is equal to n in this case, that since it is equal to mi, we have this relationship. And in this case, when we look at this sigma I matrix, A minus lambda I identity, then its null space is going to have a very, very specific structure. Sigma I square. Remember, we know that this is going to continue until null space of sigma I mi. And I know that the dimension of this thing is ri, which is equal to mi. And the dimension in general is equal to ri, but in this case we have the equality between ri and mi. Okay? And remember, in the last lecture we have seen that the dimensions of these ones should be 1, 2, and I have mi minus 1 and mi. Okay? In this case, therefore, we have one Jordan block. We have one Jordan block with size equal to mi. Okay? So I have this property. So the Jordan canonical form of this matrix is just this one, lambda I on the main diagonals and ones above the main diagonal, and I would have zeros everywhere else. So I know that this should be an n by n matrix. So you can also say that mi is equal to n. That is why we have one Jordan block with size n by n here. All right. So this was the Jordan canonical form of such a matrix, and in this case we know that mi is the size of the largest Jordan block, and in the Jordan canonical form. And I have here the Jordan canonical form has only one block for the eigenvalue lambda I, and the size of it is mi by mi, which is equal to n by n. All right. So now we have then talked about how to find a basis for this largest null space. And in that case, remember, we have only a single chain of vectors. So I have these concentric null spaces, null space of sigma I square, null space of sigma I mi minus 1, and I have null space of sigma I mi. Okay, and the dimension of this thing is mi or ri or n. Okay, so I have the largest null space equal to Cn in this case, because these null spaces are always subspaces of Cn, and since the dimension of the largest null space is n, it has to be equal to Cn. All right, and remember that in this case we have only a single chain of vectors. I choose an x in the largest null space, sigma I and mi, and x is not in null space of sigma I and mi minus 1. Okay, and in that case this vector has its continuation, sigma I x here, until I reach the eigenvector inside the chain, mi minus 1 x. Okay, so this chain of vectors it would be formed from m vectors, and I have sigma I x here. The first one is the eigenvector corresponding to that chain, and The others are generalized eigenvectors. But here I have mi vectors. That means that I have n vectors in Cn, and these should be linearly independent by the theory that we have seen. And since I have n vectors, then that means that, and since I have mi vectors, and since the dimension of this space is mi, in that case, this single chain becomes a basis set for the largest null space. Okay? And that means that I can form my P matrix out of these basis vectors. Sigma I, x, and this P would be invertible. And then if I obtain this A bar, which is P inverse AP, it is going to turn out to be the Jordan canonical form that we had here. Okay? So this was the first special case, which is one of the extreme cases. And the second case is going to be the other extreme of the similar picture. Okay? So let us look at case 2. In this case, again, we have A in Cn by n, and we have, again, single eigenvalue, lambda I, and in this case, d of s is s minus lambda I Ri, and m of s is just this one, s minus lambda I. So the minimal polynomial power mi, minimal polynomial, is a first order polynomial. So I have mi is equal to 1. All right? So now we are wondering what is going to happen in this case. Okay? As I told you, this is the other extreme case. So remember, mi is actually the size of the largest Jordan block. So in this case, mi is equal to 1. So in this case, I need to have the size of the largest Jordan block corresponding to such a matrix would be 1. Okay? So the largest Jordan block has size 1. That means that all of the Jordan blocks has size 1. So that means that in this case, this matrix is going to be diagonalizable. Remember, we have seen the fact that a matrix is diagonalizable if and only if all of the powers in the minimal polynomial are equal to 1. Okay? Or we have seen that a matrix is diagonalizable if and only if it has n linearly independent eigenvectors. So as many linearly independent eigenvectors as the size of the matrix. Okay? These are the conditions for if and only if conditions, sufficient and necessary conditions for diagonalizability. And in this case, we satisfy those criteria. Let us try to see. So in this case, characteristic polynomial should be an nth order polynomial. That means that this Ri is equal to n. Okay? So now let me try to write these null spaces. So null space of, if I define sigma I, A minus lambda I identity, then null space of sigma I. So is this null space going to grow when I increase the power, null space of sigma I square? In this case, there won't be any growth. Okay? Because the largest null space is reached at the power of the minimal polynomial for the same eigenvalue. Okay? So this is the largest null space and its dimension is Ri. Okay? And the dimension of this one is still Ri because it's the same space. So in this case, how many Jordan blocks would I have? Let us find the Jordan canonical form for such a matrix. As I told you, since mi is equal to 1, Jordan canonical form has to turn out a diagonal matrix. So let me try to find the Jordan canonical form of that matrix. First of all, how many Jordan blocks? We know that the total number of Jordan blocks is the dimension of this null space, dimension of the eigenspace. So I have number of Jordan blocks is equal to, I would have in this case Ri, dimension of the first null space, and I would have in this case Ri, and this is equal to n. So there would be n Jordan blocks. And what about the size of the Jordan blocks? I know that this difference of the first two null spaces would give me the number of Jordan blocks whose size is larger than or equal to 2. Okay? So I have number of Jordan blocks with size larger than or equal to 2 is going to be the dimension difference, which is going to be 0. So there are no blocks with size 2 or larger. Actually, this is already told to us by the minimal polynomial power of this eigenvalue. I know that this power should be the size of the largest Jordan block, which is 1. That means that I would have only blocks with size 1 here, because the size of the largest Jordan block is 1. Okay? So that means that we have Ri Jordan blocks. So we have Ri Jordan blocks with size equal to 1. Okay? In this case, this is my condition for the Jordan canonical form. And if I try to write this Jordan canonical form, then it's going to be lambda I, this is a 1 by 1 block, lambda I, 1 by 1 Jordan block, and I'm going to continue like this, lambda, and this is my last block. Okay? So this is Ri by Ri, or n by n, because Ri is equal to n. All right? But do you see that this is a diagonal matrix? Okay? When the Jordan blocks have all size 1, the Jordan canonical form turns out to be diagonal. And that means that this is a diagonal matrix, and actually, since all the diagonal elements are equal to lambda I, this is equal to lambda I times the identity matrix. Okay? So now let us try to find the P matrix that would put this matrix into its Jordan canonical form. So I would have only a single null space. That is the largest null space of sigma I. Okay? So then our chains, remember the size of the chains are determined by the number of concentric subspaces here. Here I have mi concentric subspaces. That was why the size of this chain turned out to be mi. Okay? But here I have only one concentric null space. That means that my chains for this type of null space would have size 1 always. So I would choose here, let us choose an x1 vector here. Okay? This is going to form one of my chains. So x1 is going to be, of course I need to choose a non-zero x1 vector in this case. And this is going to be x1 is not equal to the 0 vector, and this is going to be my first chain. Okay, I know that this null space has dimension Ri, and which is equal to n. Okay, so do you think only a single chain would be sufficient for us to find the P matrix in this case? So do you think a single chain would be sufficient for a basis set for this overall null space? If the null space, if Ri is equal to 1, then yes, this is going to be sufficient. But if Ri is larger than 1, then a single chain would not be sufficient. So how many more chains do I have to find? I need to actually continue until I have Ri linearly independent vectors in this set. Okay? So I have here a single chain. So this is my first chain of size 1. And in that case, I had only one chain. This was the first chain of size mi. Okay? And we didn't need any more chains because Ri was equal to mi in the earlier case. But here, this Ri does not have to be equal to the size of this chain, which is 1. That is why I need to continue finding chains which would complete the set of total number of vectors, to linearly independent vectors to Ri here, which is the dimension of this null space. Is this x1 an eigenvector? In this case, do you think this x1 vector that I can find here, it's an eigenvector for lambda I? The answer should be yes. This is the eigenspace. So any non-zero vector in that eigenspace would be an eigenvector. Okay? So now this single chain is not sufficient to form a basis vector for this largest null space in this case. That means that I need to continue finding additional chains here. So I'm looking for another vector here, x2, which is going to form another chain. And the size of that chain would still be 1 because the number of concentric null spaces here is 1. Okay? So x2, I need to have x2 non-zero, and there should be also another condition, right? If I choose x2 exactly equal to x1, then these two would not form a linearly independent set. So I cannot form a basis if these two are linearly dependent with each other. So what I need to do here, I need to choose x2 such that it is linearly independent with x1. Okay? So this is our second chain of size 1. All right? And I'm going to continue in this manner until the total number of vectors that I find here reaches the dimension of this null space, largest null space. Okay? So I'm going to continue until I reach xri here. Or instead of xri, I can call this as xn because ri is equal to n. Okay? So I find xn here, and xn is not equal to 0, and xn is linearly independent with all the other vectors that I've found previously, x1 to xn minus 1. So I have this, and this is my nth chain of size 1. Okay? Now if I find linearly independent vectors and linearly independent vectors in the same null space, and each of those, the set of each of those vectors would be a chain of size 1, and if I combine these vectors inside these sets into a single set, it is going to form a basis for this null space, and then I will be able to fill in my P matrix. So here, these are my chains. I have n chains of size 1. Look at the Jordan canonical form. In the corresponding Jordan canonical form, I had n Jordan blocks with size 1. In the earlier case, I had one Jordan block with size mi, and I had one chain of size mi. Okay? So you see that there is a match between the number of Jordan blocks and the size of, and the number of chains, and the sizes of the Jordan blocks and sizes of the chains. So here I have n Jordan blocks with size 1, and I had n chains with size 1. Okay? One Jordan block with size mi, one chain with size mi here. And here I see that each of these vectors that I can find here is an eigenvector. Okay? So I have x1, x2, xn, they are all eigenvectors. Okay? Why is that? Because they are living inside the eigenspace, null space of sigma I. So, and they are non-zero, and furthermore they are linearly independent. So in this case I have found n linearly independent eigenvectors. This also tells me that this matrix should be diagonalizable, meaning that its Jordan canonical form is diagonal here. So that is an equivalent condition. So now I can fill in these vectors into my P matrix. So I have x1, x2 going until xn. Okay? So this is going to be an invertible P matrix because it is composed of n linearly independent columns coming from Cn. So that means that this P matrix is invertible. And now I can look at what A bar is. A bar is P inverse AP. Equivalent form of this equation is P times A bar is equal to A times P. Okay? So if I write this P here, x1, x2, going until xn, then this is my A bar. I want this A bar to be equal to the Jordan canonical form, and that is going to be equal to A times P itself, x1, x2, going until xn. I know that I can make this multiplication on the right, and that is going to give me A times x1, A times x2. These are the columns of the multiplied matrix, A times xn. Okay? So you see that in order to be able to find this A bar, I need to express A times x1 as a linear combination of these columns. Then the coefficients would form the first column of A bar. Then express the second column here as a linear combination of the columns here. And the coefficients would be the second column of A bar. This is P. And this is P. I've told you that this A times x1 should be an eigenvector. All of these vectors are eigenvectors. So let us see that. All of these vectors are in null space of sigma I. So I know that sigma I times any vector there, xj, is going to be 0. Okay? That means that A minus lambda I identity times xj is equal to 0. But this means that A times xj is equal to lambda I times xj. Okay? If I expand that multiplication and take lambda I xj to the other side, I would get this. And since all of those xj's are actually non-zero, they should be eigenvectors. All right? For the eigenvalue lambda I, of course. And now I'm here about to explain or express this A times x1 as a linear combination of these columns here. A times x1 is lambda I times x1 because x1 is an eigenvector corresponding to the eigenvalue lambda I. So what should be the coefficients expressing AX1 as a linear combination of these columns here? Obviously the first coefficient should be lambda I and the rest will be equal to 0. A times x2, x2 is an eigenvector. That means that A times x2 is lambda I times x2. So the coefficients would be 0, lambda I, 0, 0, 0. 0, lambda I, and all zeros, the rest. So this is correct for any of these columns here. So I would have here all zeros at the end with only the coefficient lambda I. So this is a diagonal matrix, and you see that it is exactly equal to the Jordan canonical form. Okay? A bar is equal to J. Okay? So now we see that this is the other end of the extreme cases. So in the first case we had only one Jordan block with the size equal to the size of the matrix, and in this case we have n Jordan blocks with size 1. Okay. So in this case, you can actually realize something quite interesting. So here, this A bar turns out to be the Jordan canonical form. So you see that this is lambda I times identity. Okay. So I have P times A bar. So let me write this equation. A bar is equal to P inverse AP. So if I extract A from this equation, A is equal to P times A bar times P inverse. Okay? So now you see that this is P and A bar is lambda I identity times P inverse. But the identity multiplication with P inverse would give me P inverse. So this would be lambda I times P inverse. Okay? But P times P inverse is identity itself. lambda I identity. So in this case, you see that the matrix itself, the A matrix itself, should be a factor of the identity matrix, lambda I identity. Okay, so that is actually a very interesting fact. So we see that the A matrix itself should be a factor of identity matrix. So here I can actually see the same thing exactly from the minimal polynomial here as well. The minimal polynomial of S was S minus lambda I. What should be M of A? M of A is A minus lambda I identity, and I know that minimal polynomial satisfies the equation M of A is equal to 0 n by n. So A minus lambda I identity is the zero matrix. Take lambda I identity to the other side. That means that A is going to be equal to lambda I identity. Okay? So this is nothing strange actually, this extreme case. So now we have finished with these extreme cases, and we are going to see that all of the other cases will be in between these two extremes. And in that case, we will see the procedure of how to find these chains of vectors in order to be able to find the P matrix. So now let us look at an example. So A is a 6 by 6 matrix, and lambda I is the only eigenvalue. And we are given some facts here. So D of S is equal to S minus lambda I to the power 6, and M of S is S minus lambda I to the power 3. And we are given also some dimensions. Dimension of null space of sigma I is 2, and dimension of null space of sigma I square is equal to 4. Okay? In this case, we are asked about what the Jordan canonical form is and what the P matrix, putting this matrix into this Jordan canonical form, would be. So now let us look at these null spaces in order to be able to find the Jordan canonical form. So I have null space of sigma I, eigenspace. Null space of sigma I square is larger, and null space of sigma I cube, can you guess what the dimension of this one should be? The minimal polynomial power is 3. That means that this is going to be the largest null space. Alright? And what about its dimension? It has to have a dimension equal to the characteristic polynomial power of the eigenvalue. So I have dimension 6 here, and the dimensions of the others are given as 4 and 2. Okay? So now let us find the Jordan canonical form. How many Jordan blocks are there? Is 2. Number of Jordan blocks with size larger than or equal to 2 is this difference. It is again 2. And number of Jordan blocks with size larger than or equal to 3 is again 2. Okay? And the number of Jordan blocks whose size is larger than or equal to 4 should be just 0 here. Okay? And here you see that since the minimal polynomial power is 3, it is going to be the size of the largest Jordan block. So size of the largest Jordan block is 3 in this case. That means that because of this, I have 2 Jordan blocks with size equal to 3. Okay? So I have this fact in this case, and no other Jordan blocks. So So now let us try to find this Jordan canonical form. So it's going to be a 6 by 6 matrix, and I would have lambda I, lambda I, lambda I. This is going to be my first Jordan block, and the second Jordan block is going to be these ones. So I will have zeros everywhere else. So you see that we see here 2 Jordan blocks with size equal to 3. I told you that when you try to find the P matrix, the number of Jordan blocks is always equal to the number of chains that you need to find, and the size of the Jordan blocks should be always equal to the size of the chains that you would find. Okay? So in this case, I am expecting to find 2 chains as the basis of this largest null space, and their sizes should be 3 and 3. So now let me draw these null spaces. Sigma I square, and null space of sigma I cube. So the dimensions are 2, 4, 6 here. And we see that null space of sigma I cube is actually C6. Because it is living inside C6 and its dimension is 6. Therefore, in this case, this is happening because we have the matrix with only a single eigenvalue. So my null space decomposition looks like this. Null space of sigma I cube. Okay? And n is 6 here. This is my null space decomposition in this case. That means that this largest null space is nothing but C6. Okay? So now let us try to find the first chain. So I'm looking for an x vector here. X is going to be in null space of sigma I cube, and x is not going to be inside null space of sigma I square. X is inside the outermost disk here, in the largest null space, but not inside the one inner null space. Okay? X is going to be this one, and then this is going to have a continuation, sigma I x here, and sigma I square x. And this is the eigenvector corresponding to this chain, and the other ones are the generalized eigenvectors. So that is going to form my chain, sigma I square x, sigma I x, and x. Okay? So this is my first chain of size 3. This is corresponding to the first Jordan block. First Jordan block with size 3. Alright? So do you think these 3 vectors would form a basis for this largest null space? The largest null space has dimension 6. Therefore, in any basis set of that null space, I need to have 6 linearly independent vectors. But in this chain, I have only 6 linearly independent vectors. That means that I will not be able to form a basis out of those 3 vectors. Their number is not sufficient. That means that I need to look for additional chain of vectors. And here, I see from the Jordan canonical form that I need one more chain with size 3 here. Okay? So when you look for an additional chain, you always try to start from the outermost disk again. Okay? So we see that the dimension increase from here to here is from 4 to 6. So actually the dimension increase from the inner space to the outermost space is 2. Okay? So I can here therefore find another vector y. This y is going to be inside null space of sigma I cube, and y is not going to be inside null space of sigma I square. Okay? Y is going to satisfy the same conditions as the x vector that we have found earlier. And then this y is going to have some continuations here. Sigma I y and sigma I square y. Okay? So that is going to give me my second chain, sigma I square y, sigma I y, and y here. Okay? So this is my second chain of size 3. Okay? So do you think all of the conditions are okay? So if I satisfy all of those conditions for these vectors x and y, then I'm done. The answer is unfortunately not. So what happens here if I choose y the same as x? If I choose, suppose that I'm really lazy, I don't find another vector here. So it is only these conditions that I need to satisfy. So why not choose y equals to x? Okay? Do you think in that case I would succeed? In that case, if you choose y linearly dependent with this x, then what is going to happen is that the vectors here in the second chain would be linearly dependent with the vectors of the first chain. Okay? So when you combine these two chains as the columns of a single P matrix, that P matrix would no longer be invertible. So for the P matrix to be invertible, it should be full column rank, it should be full row rank. Okay? A square matrix, for being invertible, we require the conditions of full column rank and full row rank. And full column rank condition would not be satisfied if I choose y to be linearly dependent with x. Therefore, while choosing y here, I need to impose some additional conditions on y. Okay? Here, it is really not sufficient that you choose y linearly independent with x. Okay? Even when you choose y linearly independent with x, these vectors, the continuation of the y and continuation of x might become linearly dependent when they are multiplied with sigma I square. Okay? So what I need here is that all of the vectors in the second chain to be linearly independent with all of the vectors in this first chain. Okay? So it is not really sufficient to choose x and y linearly independent and then think that everything would be okay. Because it might not be okay actually if this sigma I square x would be linearly independent with sigma I square y. When you obtain the continuation of x and y, the resulting vectors should be linearly independent with all of the other vectors as well. Okay? So in this case, there is an interesting sufficient condition that you can try to enforce here, and that condition is that if you choose, suppose that you chose a y, and then suppose that you have obtained this continuation, if the vectors in the innermost space, if the vectors in the eigenspace, if they are linearly independent, then you can show that all of these chains would be linearly independent. Okay? So choosing x and y really would not be sufficient for the chains to be linearly independent sometimes. But choosing x and y such that these innermost vectors would be linearly independent is sufficient for making these two chains linearly independent. Okay? So that is the condition that we need to enforce. Here I am not going to prove that it's a sufficient condition, so unfortunately you will have to blame me on that. Okay? If you choose x and y such that the innermost vectors of the chains would be linearly independent, then these two chains would be linearly independent automatically. All vectors in the chains would be linearly independent. If you choose x and y such that the innermost vectors in the innermost space are linearly independent. Okay? So here the condition that you need to enforce here is that the innermost vectors in the innermost space, they are sigma I square x and sigma I square y should be linearly independent. Okay? If this condition is satisfied, if the vectors in the innermost space are linearly independent, then you can actually prove that all of these chains should be linearly independent. In that case, you are safe. Okay? So here I can write here the fact that vectors of the chains in the innermost space should be linearly independent. Should be linearly independent for the chains to be linearly independent. Okay? So if you choose X and Y with these conditions, then you make sure that these two chains are linearly independent, and then you can fill your P matrix from the vectors of those chains. So I fill my P vector to be the following, P matrix to be the following: sigma I square X, sigma I X, and X. This is corresponding to the first Jordan form, first Jordan block there. And I have sigma I square Y, sigma I Y, and Y. This is going to be my P matrix. All right? And it is going to be invertible because we ensured that all of these vectors in this chain are linearly independent with each other. So this is going to be a 6 by 6 matrix, and it is going to be invertible. Okay? So now just in order to be able to illustrate the procedure better, I will consider the same question by changing it a little bit. Okay? So here I will erase these. And I will solve the same question with the following dimensions. So these are going to remain the same. So suppose that I have this 3, 5, and 6. Okay? So let's say this is 3 and this is 5. Okay? So now let us try to do the same things here. So I would erase some parts here. This is going to be 3, 5, 6. In this case, what is going to change? So suppose that I have these dimensions, and in this case, suppose that I would like to find the chains and the conditions for the vectors in them. So first, let us find the Jordan canonical form. So number of Jordan blocks, I think you need to be able to answer this by now. It's going to be 3, and number of Jordan blocks with size larger than or equal to 2 is this difference, 2, and number of Jordan blocks with size larger than or equal to 3 is this difference, it is 1, and number of Jordan blocks whose size is 4 or larger would be 0 again. Why is that? Because the size of the largest Jordan block is still 3. Okay? Minimal polynomial power is 3. So now I can say that one Jordan block with size equal to 3, okay, and one Jordan block with size equal to 2, this difference, and one Jordan block with size equal to 1, okay. So now I see that the Jordan canonical form would be looking like this. So if you didn't understand why these are so, think about these quantities. You would be able to do that. So there is one Jordan block with size 3. So I would have these. And I would have here a Jordan block with size 2 and a Jordan block with size 1. So in this case, I have this 6 by 6 matrix as the Jordan form of this matrix. Okay? So now, how many chains do you expect, and what should be their sizes in the P matrix? If you try to find the P matrix, you're going to see that you need 3 chains, and their sizes should be 3, 2, 1. Okay? So we have here number of Jordan blocks is equal to number of chains, and size of the Jordan blocks would always be equal to the size of the chains. Okay? We always have these equalities. So now let us try to find the P matrix. So in order to be able to find the P matrix, I'm going to start here. So that is going to give me an X vector. X is going to be inside null space of sigma I cube, and X will not be inside null space of sigma I square. All right? So now, this is going to give me my first chain if I obtain the continuation of X. So I have sigma Ix, and I would have sigma I square X. Okay? So I would have sigma I square X, sigma Ix, and X here. A chain of size 3 corresponding to this Jordan block. Okay? And now I know that this is not sufficient for being a basis set for the 6-dimensional largest null space. Okay? So that means that here I need to find additional chains. There are only 3 vectors here, but the dimension of the overall space is 6. So I need additional chains here. So how to find those additional chains? So I'm going to do a similar thing. I will try to find a y vector, and I will try to find the y vector by starting from the outermost disk. Okay? Do you think I can find a y vector in this outermost disk? So here I see that the dimension increase from this null space, from the inner null space to the largest one, is from 5 to 6. Okay? So this dimension increase is just 1. Okay? So do you think I can try to find a y vector here in this outermost disk? It is not going to be really possible here. Okay? So even if I find a y vector here, then when I obtain its continuation, I would always obtain linearly dependent vectors with the first chain here. Okay? So I will not be looking for the y vector here, because this dimension increase from 5 to 6, it means that there is only space for one vector in this outermost disk. Okay? And that is the vector x. Okay? So I won't be looking for my y vector in the outermost disk here. Instead, I will try, since there is no space for the y vector here, I will go one space inside, and we'll check if there is space in the inner disk. Okay? So this increase from this innermost null space, from the eigenspace dimension to dimension of null space of sigma I square, is from 3 to 5. So that means that there is a space for another vector here, because this dimension increase is just 2. So I'm going to choose my y vector here, because it is the first disk in which there is space for an additional vector. So I will choose y inside null space of sigma I square, and y is not going to be inside null space of sigma I. Okay? So this y should satisfy this, and y needs to have a continuation, sigma I y here. Okay? And are these the only conditions? Definitely, when I form the chain corresponding to this y vector, it is going to be a chain of 2 vectors, because it started here, y here, and sigma I y is its continuation. And this has to be the eigenvector. So in this case, my new chain will be of size 2. Okay? And I want this chain to be linearly independent with the first chain. And we now know the condition, you believed me, that this condition is that I need to make the vectors inside the innermost disk linearly independent. So the additional condition here is that sigma I y and sigma I square x should be linearly independent. Okay? If I make sure that these first vectors inside the chains are linearly independent, then I can be sure that I really do not have to check if x and y are linearly independent, or y and sigma x are linearly independent or not. Okay? If I make sure that the vectors in the innermost disks are linearly independent. Okay? So this is my additional condition. Sigma I square x and sigma I y should be linearly independent. Okay? then I have my second chain of size 2. It is the chain corresponding to this canonical Jordan block, okay? 2 by 2 Jordan block, 3 by 3 Jordan block chain, and 2 by 2 Jordan block and chain. And I would have here an additional chain with length with size 1, okay? So now, are these 5 vectors sufficient for being a base for forming a basis vector for the overall space? The dimension of the largest null space is 6, but I still have 5 vectors here, okay? So these are not going to be sufficient, even when all of them are linearly independent. They won't span that null space. So as a result, I need to look for an additional chain here. And how to start that chain? In the outermost disk, there is no space to start that chain. In this disk, I have already found 2 vectors, and this dimension increase was from 3 to 5. So there is no more space in this middle disk here. So I go 1 space inside, even more. So I go to the null space of sigma I go to the eigenspace, okay? The dimension of that space is 3, and I have already found 2 vectors there. All right, so there is one more space for a linearly independent vector. So I find there Z. All right. So Z is going to be inside null space of sigma I, and Z has to be, of course, non-zero. And what are the conditions? What are the additional conditions for Z? So this Z is going to form a single chain of size 1, okay? And the additional condition should be Z should be linearly independent with the other vectors in the innermost disk, okay? So I need to have Z, and I need to have sigma I square x and sigma I y should be linearly independent. This is the vectors in the innermost disk should be linearly independent condition. So you see that my third chain has size 1, and that means that I have completed the total number of vectors in my chains to be 6, which is the dimension of this largest null space, and that actually finishes my task of finding the P matrix. So now I can form my P matrix just like this. Sigma I square x, sigma I x, and x, and I would put here the second chain, sigma I y, y, and I put the third chain, which is Z. This is going to be now a 6 by 6 matrix, and you see that I have ordered the chains in the same order as the corresponding Jordan blocks, okay? What would happen if I took this chain of 2 elements to the beginning of P? In that case, these 2 Jordan blocks would change their places. What would happen if I took the last chain of size 1 to the beginning of the P matrix? In that case, this chain would jump, this Jordan block would jump to the upper left corner of the Jordan blocks, okay? And what would happen if I change the order of these chains? If I write this instead x sigma I x and sigma I square x, y sigma I y, and z. In that case, we have seen that these ones would jump below the main diagonal, okay? And that would also in Jordan canonical form according to some textbooks, all right? But it all depends on this P matrix here, okay? So how many linearly independent eigenvectors does this matrix have? What is the maximum number of linearly independent eigenvectors of this matrix? In this case, linearly independent eigenvectors means that what is the dimension of the eigenspace? Maximum number of linearly independent eigenvectors. This is the same question as asking what is the dimension of the eigenspace? And in this case, the dimension of the eigenspace is 3. That means that this matrix has at most 3 linearly independent eigenvectors for the eigenvalue lambda I. All right? And we see that what are those eigenvalues? They are already inside our P matrices. So this is an eigenvector, this is an eigenvector, and this is an eigenvector. They are the vectors inside the eigenspace, inside the innermost disk. And actually what you have to do when you try to find your chains is that you try to make the eigenvectors of the chains linearly independent. Okay? If you can make the eigenvectors of each chain to be linearly independent, then that is the same condition as this one. That is the same condition of making the vectors inside the innermost disk linearly independent. Vectors inside the innermost disk are nothing but the eigenvectors. Okay? So you see that I have, so here I can write maximum number of linearly independent eigenvectors is always equal to the dimension of null space of sigma I. For lambda I is equal to dimension of null space of sigma I. Okay? But dimension of null space of sigma I is equal to the number of Jordan blocks. Okay? This dimension, we know that, is equal to the number of Jordan blocks. Jordan blocks for lambda I. Okay? But we know that this is also equal to the number of chains for lambda I. Number of chains for lambda I. Because in each chain there is a single eigenvector. The maximum number of linearly independent eigenvectors would be the number of chains. Because in each chain the first elements are eigenvectors. Okay? So here in the lecture notes there is one more example. I have already solved some example, some parts of that example here in these videos. So as a result, I won't be able to solve that example in these lectures to actually cut the time necessary for it. Instead, in the next lecture, I'm going to be solving a numerical example, and that numerical example is going to illustrate this procedure on a specific 4x4 matrix. Okay, in that case, so if you didn't understand about this procedure here or these conditions, in the numerical example, which is going to be the final thing that we are going to do in the concept of Jordan canonical form, then you will be able to understand these concepts better on the numerical example. So once we finish that numerical example, we are going to have two more topics in this course. Each that would take approximately 2 hours of lectures. And those two topics will be the topics of Hermitian matrices and the topic of function of a matrix. So they are going to be short topics, and you're going to see actually that when we try to apply this theory to Hermitian matrices, everything would be really perfect. Okay? So we will see, for example, that Hermitian matrices are always diagonalizable. That means that the minimal polynomial powers of the Hermitian matrices would always be equal to 1. Okay? And we will see that we will be able to find P matrices that would diagonalize actually the Hermitian matrices, and we are going to see that the P matrices will not only be composed of linearly independent columns, but we will see that in the case of Hermitian matrices, the P matrices, we will be able to find P matrices with columns additionally orthogonal to each other, not only linearly independent. Okay? So we will see that the Hermitian matrices would be the vanilla version of this theory, where everything would fit perfectly, and we are going to get diagonalizability. We are going to be able to get P matrices with orthogonal columns, etc. So everything would be in their best version when we see the Hermitian matrices. And then we're going to see the final topic of functions of a matrix. In that case, we're going to see what would be how we can define the exponential of a matrix or sign of a matrix, which are actually very important in the in control theory, for example, if you are working on dynamical systems, exponential of a matrix A is going to be very, very important. And if you don't know the function of a matrix topic when you work on dynamical systems, then you would be really in trouble in control theory. Similarly, in stochastic processes, if you are working with Markov chains, for example, in that case, the Jordan canonical form would be very, very important, and the powers of a matrix would be very, very important. So if you are working on stochastic processes in signal processing, for example, in statistical signal processing, then the function of a matrix concept will be very, very important. But these are going to be for the remaining lectures. But that's all for this lecture. Thank you for watching. Bye-bye.